Welcome back again. So, TÜBİTAK Research Institute for Fundamental Sciences has had this outreach program, organizes scientific Türkiye public lecture series to share the passion for science and technology with wide audience and to foster scientific curiosity and excitement in the society. As part of this lecture series, Professor Isao Tanaka has kindly agreed to give public lecture using this school. Data-driven methods, impacts of data-driven methods on technology. With this, I want to invite Professor Isao Tanaka to the stage to begin his talk. I am sure he will be a great talk. Please be welcome.
Okay, thank you for kind introduction, and it's my great pleasure to give a talk here. I'm going to talk about impact of data-driven methods. This I have already shown that we are already in a new era of data-centric material science. We are in the fourth paradigm. Probably if you hear about the use of AI, you found something called ChatGPT is quite useful. And probably some of you as a student already use that to write down some reports instead of yourself. And it is quite useful, it's true. Of course, senior researchers think this is useless, or sometimes producing too much fake. But, well, I have some mixed feeling. And in conclusion, I think that algorithm or theory behind that is already very well made. The only thing which is lacking is data. I will show some example. I asked ChatGPT, what is the current version of ChatGPT? This is very simple answer. The ChatGPT is 3.5. And I asked again ChatGPT, please suggest any chemical compression relevant for new inorganic crystal. And the answer was, well, he said some gallium selenium nitride. And he also showed some of he or she, I don't know. It suggested some synthesis condition, etc. And well, I was quite uncomfortable as a data scientist. This is something not really realistic. So I asked another question. I do not think gallium selenium nitride is likely. Can you suggest something different? And the answer was, of course. Here are a few more hypothetical chemical compression of new organic crystal, lanthanum and boron 2O, copper Fp3, and many others. Those materials, I cannot judge whether they are really useful or not. It's difficult to say it's a fake or not, but they suggested something. And the other question I asked was, among new compounds you suggested, which one shows the best thermoelectric property? And the answer was quite honest. I do not have access to real-time data or the ability to predict property of hypothetical compound, so I cannot provide specific information about thermoelectric property of the compound. No, it's very honest. If you are interested in exploring some electric property of specific compound, you might need to consult research literature, scientific database or material informatics tools that provide data and prediction related to material properties. Yeah, this is what we believe is useful. So, for example, ChatGPT is not only producing fake, but well, sometimes it's quite useful or sometimes quite honest. But we realize that it is true that we need data. So this is also I have shown before, but there are several databases available. In the morning of today's lecture, I talked mainly about first principles calculation, but here I will talk a little bit about first principle calculation again, based on harmonic problem calculation, but the rest of the time I will talk about using of this type of database, experimental database. Yeah. So we have a long history of first principles calculation, and now we can get some information by phone, and also database can be constructed. In the chapter 1, I will talk about discovery of new low thermal conductivity materials using first principles harmonic lattice dynamics calculation and Bayesian optimization. The people who were involved in this study was those people, mainly this Professor Seko and Professor So this is also the figure I have shown before. This is the experimental lattice conductivity for a number of different systems. And the diamond has the highest thermal conductivity, which shows 2,000 in a unit of watt per meter calorie at room temperature. And window glass or SiO2 has a very low thermal conductivity, which is lower by a factor of 1,000 or even lower. Our motivation was to find out some ultra-low thermal conductivity material which is much lower than SiO2. The level much lower than SiO2 if it exists. With N material project database which contained at that time 55,000 crystals. So we use that database and we use our thermal conductivity calculation result as a database and to search something new. So probably you know that the some electric materials are very important, especially these days. Global warming is a really important issue. And in Japan, in Osaka, in Kyoto, where I'm living, every day the highest temperature exceeds 37 degrees C. So even staying in the room, our temperature exceeds our blood temperature, so it's really serious. And I don't think it is only due to global warming, but of course global warming is really making that type of trouble. And to solve a part of that problem, we need to utilize some kind of some electric material which can really convert the waste heat to the electricity. And the performance of some electric material is given as this ZT value. And here the thermal conductivity is located. So if you can decrease the thermal conductivity, it means there is a possibility to increase this figure value. Of course, the simple calculation showed that if we decrease the thermal conductivity by a factor of 10, we can increase the figure merit by a factor of 10. But of course, things are not that simple. But at least it is worthwhile to search some new material. The origin of thermal conductivity or thermal resistivity is also explained in the morning. That is a phonon-phonon scattering. So harmonic phonons do not interact. But if there is a phonon-phonon scattering occur, then it can produce thermal resistivity. So we need to compute phonon. scattering. And Professor Togo made this from a 3-type program, and it is useful for a variety of calculations. This is the result. This is also I have shown in the final as a final slide of the morning session. And this is LTC, lattice thermal conductivity. Lattice thermal conductivity of LTC at 300 Kelvin. The horizontal axis experimental data, the vertical axis is a computed result. And most of them are on this diagonal line. And well, the experimental thermal conductivity data are not always correct. And there are wide scattering among experimental data. So we believe that at least our calculation is reliable, whose accuracy are comparable to the experiment. So we take that data as a starting point. The only problem of this type of calculation was this we need to compute all phono scattering. So it is 2 or 3 order magnitude more expensive calculation than the simple phono calculation. It is very expensive calculation. The computational cost was something like 1 day for one crystal with 104 PC. 104 PC is we can make it with already many cores on the CPU, so you do not have to put so many PCs in parallel. So this is not a big supercomputer, but still it takes quite a long time, 1 day. So if you want to compute millions of crystals, you need a long time to do that. So we cannot do exhaustive search over all different crystals. Instead, we need to use some kind of machine learning technique for artificial intelligence. Before that, there is a physical model of the thermal conductivity. Slack proposed a model for the thermal conductivity based on his analysis and mass, volume, by temperature, Grignard parameter. There, they create some laws. Actually, we computed this quantity based on the Slack model, and also the by temperature and Grignard parameters were obtained by our own calculation. And it's true that many of data are on this diagonal line. It means Slack model is no bad. It is quite good. But at the same time, there are some outliers which do not follow this diagonal line. Since we are interested in proposing some new compound which shows low thermal conductivity, it means we are interested in this zone. We are not interested in those materials, but rather than that, we are interested in these outliers. So in order to predict those outliers, you can understand this type of model is not very useful. We have to do something different. So that is based on the syndrome. So these outliers cannot be found just by a model based on harmonic form. This model is based on harmonic form. But we have to seriously take it unharmoniously. Okay, so this is the so-called virtuous screen. We have some initial data. Actually, we did thermal conductivity calculation for 100 crystals. And we use some model and predictors or features, whatever, to have some kind of estimate based on a similar model. And to go through a library data which contains 55,000 of crystals in the library, to go through that with this model and predictor without making any first principles calculation in this stage to pick up some of the candidate. And this process is very important because this screening does not use any of the first principles result, just by using some of the model and predictors. So these candidates are not necessarily correct answers, but they can be candidate, and we made validation. Because this model is not necessarily good, sometimes it is validation result failed. Then we put this result to this model again and improve the model and go through the library again. So the model can be iteratively improved. This process is called Bayesian optimization. And even when we make this cycle for 100 times, 100 model and 100 cycle of iterations, you need only 200 times of the first principles calculation. It is much more efficient than exhaustive search of all compounds in a library. So we took this strategy. So in order to make this machine learning model, we need model and predictors or features. Other descriptors, we can choose many different kinds of descriptors, elemental descriptors, structure descriptors, and so on. But at the very beginning, we tried the most simple descriptors for element. Element or compound. That is, one is volume, the other is density. Of course, if we plot the volume versus, volume is crystalline volume, versus lattice thermal conductivity, the equation is not so good. The equation factor is minus 0.6. The equation is quite bad. Many people may think that if the equation is so bad, it is not useful. The equation here is much worse. It's almost no correlation. But then we use them as a parameter, as a feature. And on top of that, we use very simple or simplest elemental features for the constituent atoms. That is the elements. So if, for example, if we treat lithium hydride, we put hydrogen 1, lithium 1, the rest of the element will be 0. This is the so-called one-hot expression of the elemental features. So in that way, we can simply, or very simply, include the elemental features. So altogether, here is 2 variables, and here is 34 elemental descriptors. So altogether, there are 36 features. And we put these 36 features in the vertical axis. Also, it looks like a 1 dimension, but it is actually 36 dimension. And the vertical axis corresponds to the output. In this case, this is the lattice thermal conductivity. And as a model, we took so-called Gaussian process regression. And with the Gaussian process regression, we can make, if there is some observed result, observation, in this case, is a computed result. The computed result here and there, then this regression can make this type of regressive result model. Not only this prediction, but also the name Gaussian coming from the inclusion of error associated with the prediction. So if the location in this feature space is very close to the observed result, then we can expect smaller error. If this is far from the observed one, the error is expected to be much larger. So all the errors are expressed by the Gaussian distribution. So this is a kind of 95% confidence interval. So of course, when it is computed, then the predicted result has no error. So in that way, we can make model prediction. So based on that, here this is Gaussian distribution, and the term here is expressed like this, and we call that z-score. The z-score can provide what is the probability to exceed this difference value. In this case, we take some example, for example, the lowest known material for the LTC, lattice semiconductivity. If it is lower than this predicted value is lower than this difference value, then this score becomes higher. Or if the error is smaller, then again this score becomes higher. So you can see that. This is the distribution. If the middle of this distribution is the same as the difference value, z equals 0. But with increase of this mean value, of course z increase. But with the decrease of the error, again z increase. So in that way, we can predict the probability of exceeding this difference value according to this z value. This is really some data scientific approach. And physicists or material scientists originally did not think in that way. They always think, or we always thought, that there is some definite predicted value, and we do not use a concept of probability. But the probability is quite often used in data science. For example, look at the weather forecast. Tomorrow in this place will be good weather with a probability of 80% or 50%, 30%. They are all prediction and not definitely determined, but just based on prediction. But we can predict it that way. So based on that model z-score, this is a predicted value of the logarithmic of the lattice semiconductivity with minus here. So the higher the score, it corresponds to the low predicted lattice semiconductivity. I'm sorry for very small, tiny characters, but I do not intend to show all of them. But this is the top 100 compound showing quite high z-score. And well, there are altogether 55,000, and just 100 of them are shown here. Just let me show only the top 10 of them. Is shown here, top 8 of them. And there are from first ranking to the number 8. It shows quite high z-scores. The chemical formula and space group are shown here. And of course, they are based on a very simple model using that one hot expression element and volume and density, which is not, it doesn't have good correlation with the lattice semiconductivity. So our intention at the beginning was to put all these data into the Bayesian optimization to improve our model. So in order to do that, we did first principles lattice semiconductivity for these compounds. Well, by the way, this number 6 is missing here. It is not by error. This is quite complicated crystal, and at that time, our computer cannot handle that crystal in time. So it was just only bit. So we did all these 7 calculations for all candidates and found that they are really not bad. Remember that we were interested in finding crystals which has lower thermal conductivity than the current one. It is something like 1. Window glass is 1 watt per meter Kelvin. So the first one already attained 0.1 watt per meter Kelvin, of course by theoretical calculation. But well, they are not bad. Actually, they are quite good. So it means it is not necessary to do the Bayesian optimization to find out something new. This is already good enough. The structure is look like that. And the good thing is they are already once synthesized and crystal structure are known. So this is not a dream, but this is just can be experimentally confirmed. But as a thermoelectric application, we worried somehow about band gap because the band gap for this material are quite high. And it may not be useful for the thermoelectric material, which should show good electric conductivity. So we have all list of 55,000 compounds and found that at the ranking number 101 to 1, there is this compound which has quite reasonable lattice conductivity with quite narrow band gap. And that this ranking, this is the one. So they may be a good candidate of lattice thermoelectric applications. Actually, our Korean colleague collaborator tried to synthesize that and try to measure the thermoelectric property. But unfortunately, those materials are not very stable in air, so they were not able to measure the thermoelectric properties. But this is a kind of method which can use theoretical result to use machine learning technique to find out something new. This is structures. Okay, so this is what we use the theoretical result for machine learning. In chapter 2, we use ICSD database to find out some new compound. Here, I need to explain 2 terms. One is recommender system. The other is chemically relevant composition. So let me explain one by one. So the database we use is ICSD data. So recommender system. This is something you every day encounter whenever you use smartphone or whatever in the daily life. If you buy something, this is something used for Turkish people. You buy something here. Whenever you buy something there, they always recommend you to let you buy something different. This is book. If you buy this book, they think that you are also interested in buying this book. If you buy some pants, then they recommend you to buy some hat together. In that way, they make pinpoint advertisement to you. It is much better, much more efficient than just putting advertisement on TV or on the wall, big wall, a big paper, or in a journal or magazine or whatever. It is not pinpoint and it is not that efficient. Pinpoint advertisement is very useful, and actually many of e-commerce is using that. That is the recommender system in data science terminology. So we use this technique. So let me explain what is chemically relevant composition. If you look at this type of databases, for example, in the pseudo-binary oxide or pseudo-binary compound, you may find this type of compound with a composition 14, 18, 614, 212, and nothing else. When you perform first principles calculations, you can find that those compounds are on the convex half. This was already explained in the morning session. If you look at the material project database, they have also this type of convex half. And here also, if we did first principle calculation, the formation energy are on the convex half. So they are thermodynamically stable compound. Some other composition like 1038, 658 are not on the convex half, and they are probably not CRC. And there is no easy explanation why 1418 is on the convex half and they are CRC and 1038 are not. There may be some kind of magic number or some other logics behind that. But before finding that type of logics, just let the computer think about that. So this is a CRC in our definition. The traditional way to discover new compound are done in the following way. If there is this type of compound registered in a database, they just use a concept of similarity, like group electronegativity or ionic radius. If the electronegativity of this element A is very similar to this element P, they guessed that this is, although it is not yet reported, they can expect that this theories also existed. In that way, people worked for a long time and for more than 100 years. And in that way, inorganic chemists did some success to find out some new compound. And we simply extended that approach, similarity approach, but using the data scientific techniques. Instead of using just one parameter like ionic radius or electronegativities, we used many different variables. Here I have shown only feature number 1 and feature number 2 as a elemental feature like ionic radius and electronegativity. But actually, as I will show later, our dimension here is 500 dimensional space. It is not possible to be shown on this slide, 500 space, but it can be made on computers. And we have data in ICSD, and if the data is available, data is registered, then compound ICSD registered compounds are plotted like that. The others are made in this grid point. They are mostly ICSD, not registered compound. But there are many possibilities for non-registered point. This can be non-CRC or just unexperimented chemical composition. Or somebody did the experiment, but since it was difficult to be formed, like the material which we need really high pressure to synthesize, or sometimes a really special technique, chemical technique to synthesize that. There are many other possibilities. So this grid point without any data need not to be non-CRC, but something different. But at the very beginning, we use this red data as a score 1, and the other point as a score 0. And we use binary classification technique. Binary classification technique is very simple. If you have this type of blue and red point like this, there are many different ways for to make the red zone and blue zone, something in between. This is called classifiers, and depending on the choice of classifiers, the results are sometimes totally different. This is very precise, but sometimes it is too much fitting to this distribution. And some of the linear and or some other, there are many different. But there is no logics behind these models. They are all models. This kind of thing is described in the data science textbook, or this was obtained from scikit-learn documentation. Scikit-learn is very well made database for the many different kind of this type of models. In the data science, just saying that there is no logic. If the result is good, then it is a good one. Again, if you think of the weather forecast, depending on the data from many different positions, they predict the tomorrow's weather. There's no much logic. I should not say it's no logic, but there's no much logic. But if some model predict better than the others, they consider that model is a good model. So we have tested everything and found out some models like logistic regression or gradient boosting, random forest performed quite nicely. So for that purpose, we use the initial data set, 33,000 ICST registered compound ionic compression. And our search space was something like 1.8 millions of chemical compression composed of these elements. For the elemental features, there are many different possibilities. If you look at this type of periodic table, put it in a wall as a wallpaper, there are many small quantities or numbers on the corresponding to each element. There are sometimes intrinsic quantity of element like atomic number, atomic mass, or heuristic quantities like Pauling negativity, Allen's electronegativity, etc., ionic radius, and so on. The physical property of elemental substances are sometimes the melting point of element, boiling point of element, something like that. Of course, you may worry that while for electronegativity and other electronegativity, they are mostly similar. But the data scientist knows how to avoid that kind of overfitting. So they normally use whatever we can use. So we use all of them. If it is not really necessary, they just avoid it automatically. Together with these 22 elemental features, we use some compound representation. If the compound is AB in the feature space, A and B are put like this, and we take average, variance, skewness, and covariance as a compound representation. This compound is made in the same way. So in that way, we end up with something like 500 elemental features. So we made 500 dimensional space, feature space. Okay, this is already the result of validation. By the way, we use ICSD data as a training data. And we need to validate the result, whether the result is correct or not. In order to validate the result, we need a kind of test set. And for the test set, we use the other database called ICDD. There are significant overlap between ICSD data and ICDD data. But we just removed overlapped part from here and just use this yellow part for the training data and the rest of the ICDD part as a training data. So there is no overlap between ICSD and ICDD. So we counted the number of compounds included in the test set as the number of correct answers, which is shown in this vertical axis, number of compounds included in ICSD. Horizontal axis corresponds to the ranking of the predicted probability from the first rank, number 1, to number 20,000 within 1.8 millions of different compositions. And as you can see, that random forest performed best among these three models. And with the decrease of ranking, this is a cumulative number. The number of correct answers somehow declined. But it is very good in the very first term. So the gradient of this curve corresponds to the number of compounds we found within each of the bin. So the first curve corresponds to the top 1,000 compounds. Among these top 1,000 chemical compositions, we found 180 among the top rank 1,000 as a correct answer. So success rate of finding compound or correct answer was 18%. This is 60 times higher than the random search. Random search can produce just 0.29%. This is quite low and this is quite high. So this is quite successful, and we thought it is more or less good enough to show to the experimentalists. And actually it is very difficult to show to the experimentalists, but we made some way to show that. And this is just blinking LEDs or boosters, but this is a pseudo-ternary compound. So 3 compound, and this compound and member is changing. And depending on the combination of these compound, the position of the recommended chemical composition, recommended CRC is changing. Sometimes you can see some red studs, and it is a very good candidate for the new CRC. So when we show this type of result to experimenters, some of them are interested. One of them are Professor Kano, who is very good in producing lithium battery materials. And he actually made very good all solid-state lithium battery with Toyota Motors. They were looking for some oxide material which shows very good lithium conductivity. For that purpose, they need a good model system which shows new structure. We gave them some of the candidates for the new CRC, and the young professor actually synthesized those pinpoint synthesis of new compound, and found that at this composition, he found this compound, which is completely new compound. And after finding this compound, they are trying to modify this by doping of different kinds of material, which is, they are very good at doing that type of system, that type of modification. And also in this pseudo-thermal, they found some different composition. So in that way, our population really motivated experimenters to do something pinpoint synthesis, similar to the pinpoint advertisement by e-commerce. The other one is actually the discovery of novel nitride. This is aluminum nitride, lanthanum nitride, silicon nitride, ternary, pseudo-ternary, and we proposed some compositions. And they did pinpoint synthesis and actually discovered 4 as yet unknown nitride and oxynitride. This is still a tiny crystal, but they already succeeded to make the analysis, crystal structure analysis, chemical composition analysis, and so on, detailed analysis of this crystal structure. Okay, so, this is the end of my talk. Well, in this way, we use the recommender system based on the database existing in ICST, trying to find something new. And in the first part, I use the theoretical result. In the second part, we use experimental database. But both of the methods, we simply use algorithms that are already existed in information technology or data science. So for the algorithm, it is not new. In other words, algorithm is already existing. The only thing we need to apply is the data. If there is a sufficient data, if we give sufficient data to ChatGPT can immediately give you a correct answer. So that is the end of my talk. Thank you very
So questions, please. Yes, please. Madam, please.
Thanks for this nice talk. I have one question actually for the first part. Did you also try bandgap as a feature during the machine learning training?
You mean the importance of features?
Yeah. Yeah, actually you said that you also tried elemental properties, elemental features. Did you also try bandgap? At the end, you are combining your results with bandgap. Therefore, I must.
Well, we didn't try to combine the band gap for the search scenario. This is everything we did. But we also made, because this model was too simple, so we tried to improve our model, and actually we succeeded to make better model than this one. Of course, this is too simple. And actually the error by the, we also estimated the error by this model and by the other model. The other model uses much more elemental feature than this one. And the result is the error was much better, something like, here the error by previous model was something like this amount, like 0.5 in logarithm scale. But if we improve the model, it becomes 0.1. So it's 5 times smaller error. But we realize that to use this type of model, we do not need such a precise model, because we want to find something new in this region. So what we need to do is just a prediction of this area, not that. And to distinguish that crystal with that one, we do not need much precise model. Anyway, we will compute the semiconductivity afterwards. So for model, we do not. So for that purpose, we realize that the use of the simple model is better for this purpose. So depending on the purpose, if you really want to compute the semiconductivity without computing any principal calculation, then you need a good model. But here, just to distinguish different crystal, we do not need. So depending on the purpose, we have to choose. And that is probably necessary to think before doing that. But we understood that after we did everything. So.
More questions, please. Yes.
Thank you for this answer. I'm actually first of all, thank you for this great talk. I'm actually from Boğaziçi University. I'm also doing some this kind of data mining and machine learning research on battery materials. But I think in my experience, my main problem was the experimental part. When we measure something, some properties, some characteristic of a material, different labs may end up with different results depending on the technique, depending on their, I don't know, their testing conditions. So how you deal with these kind of differences in the measured variables, even if the materials are the same? Maybe the material characterization, maybe material synthesis may be different. That will end up very different results. I also have this problem, and I am getting difficulty by dealing with these kind of problems. For example, you said there are two different databases, or enumerated databases, and you said there are overlapping regions. How similar were these results there?
Well,
There's a long question.
Well, I perfectly agree with you. The experimental data is very much, we have to be very much worried about how they did that experiment. And depending on the experimental condition, the results are sometimes quite different. And for these crystal structures and this ICSD database, they examine what the database producers examine many different literatures and put most reliable data. So it is quite useful. But for the other data, property data and so on, it's very much scattered. So my conclusion is that it's probably better not to rely too much on the literature data, but to design some measurement system by myself or by the other people who systematically produce experimental data under same condition. Otherwise, if the data, this data is from this group and the other data from the other group, they are not always comparable. Sometimes comparable, but we always have to worry. So I think that is important when the number of data is very small, if it is 100 or 1,000. If the number of data is huge, like millions or billions, like in e-commerce, then if there is some noise or something, it can be ignored. But if we handle only small data, then we have to worry about the quality of data. And the experimental data are not always that quality, in my opinion.
More question, please.
Is this method just used to find new compounds or can it be used for developing new alloys for composite materials?
I don't know.
Is this method just used to discover new compounds or can it be used also for developing new composite materials and alloys?
So, first of all, I should say that it's useful to propose some new composition, not to discover. If we really want to discover, we have to do experiment to really confirm that this prediction is useful. So we're not discovering something. So I sometimes use the term discover. But anyway, we proposed some of the candidates. And basically, this method is useful not only for prediction of new compound, but for many other purposes, but always quality and quantity of data. If the data is not sufficient, if you want to predict some material with good property, you need some property data. Otherwise, it's possible as ChatGPT answer. So it's all depends on the data.
Thank you. One more question, please.
What is the computational cost for the latest tertiary phase experiment and your prediction?
You mean the computational cost for the experiment versus the computation?
Computational cost of the estimations.
Oh, computational cost is here is 1 day walk clock time using this computer. So
It's a high performance computer.
no, just 100 core PC, and probably you have the ordinary PC has 16 or sometimes 32 cores. So it's just depending on when you did the calculation. At that time, probably we use 8 core PC, so we made parallel 12, 10 or 12 PCs. But now you have many more cores on one PC, and that can be done by chip.
GPU type.
Well, GPU can also be used, but at that time we didn't use GPU. So computational cost is not that much as compared with experimental. Experiment is very expensive. This is relatively cheap. Even for single PC using this type of PC, it takes 1 days.
Okay. If no more questions, let us please thank the speaker once again for this very nice and exciting talk.
Okay.